Hello, my name is Pavel Panteleev. This is joint work with Gleb Kalachev. We are both from Mechanics and Mathematics Department of Moscow State University. The title of my talk is Asymptotically Good Quantum and Locally Testable Classical LDPC Codes. Okay, our plan. So first we start with the definition of classical LDPC codes, then we define quantum LDPC codes and locally testable codes. Then I'll describe our general constructions called lifted product, and I'll talk about our proof ideas, and I also talk something about some further directions. Okay, classical LDPC codes. A classical LDPC code is just a standard linear code defined by a sparse parity check matrix. And each linear code has two important parameters called dimension and the minimal distance. And LDPC property just means that this parity check matrix is sparse. One usually represents LDPC code by the corresponding bipartite graph called Tanner graph, where we have one part that corresponds to bit and another part that corresponds to checks. The simplest example of a classical LDPC code is a repetition code. Here we have n bits and n checks, and each check just says that these two bits are the same. It is helpful to consider classical codes as a subspace of a space FQN, and the distance has a simple geometrical interpretation as a minimum Hamming distance between different code words, elements of the space C. Classical LDPC codes were introduced by Gallagher, and nowadays they're used almost everywhere. And what is important about classical LDPC codes that it was shown by Gallagher that there exist asymptotically good families of LDPC codes, which means that the dimension and the distance both grows linearly with the number of bits. And what is even more important, that later in 19th, it was shown by Sipser and Spielman that these codes can be constructed efficiently, explicitly, and they also may have linear time decoding and encoding. Okay, let us discuss quantum LDPC codes. We can see the quantum LDPC codes from special subclass of codes called CSS codes, and a pair of this kind of codes is defined by a pair of classical LDPC codes, which we denote by CX and CZ. And the reason why we have two codes instead of one is because in the quantum world, we have two kinds of errors. So first kind of error corresponds to the standard classical bit flips. And we also have some other type of error called phase flips. And this is why we need two codes to protect from both types of these errors. And we also cannot use arbitrary codes. So their parity check matrices should satisfy some special orthogonality or commutativity condition. And this condition just says that every row of the matrix, parity check matrix HX, is orthogonal to every row of the matrix HZ. And here a star just means the transpose. One usually represents quantum LDPC code by its Tanner graph. And here we have three parts, two parts for Z checks and X check, and one middle part for qubits. They have some parameters similar to the classical counterpart. So we have the number of qubits, it's the length of the code, and we also have the dimension, it's just the dimension of this quotient space. And we also have the minimal distance, and this distance may seem different, but in fact, it is helpful to consider these quantum codes as some quotient spaces with quotient Hamming matrix. So in this quotient space, we have cosets, and we call these cosets code words. And the minimal distance is just the distance, minimal distance between different cosets. And the famous example of a quantum LDPC code is a Kitaev toric code. It is usually represented on a two-dimensional torus. And what is important that this distance that we define here, it corresponds to the length of the systole. The systole is the smallest non-contractible loop in this torus. Quantum LDPC codes have many interesting potential applications, and the most important of them is they can be used, potentially can be used in future fault-tolerant quantum computers. And the main theoretical problem in this area is so-called qLDPC conjecture, which asks, are there any good families of qLDPC codes? Okay, let me briefly describe the history of quantum LDPC code. So I already mentioned toric code. Then there were two another constructions which in fact slightly improve the minimum distance, but it is still was around square root of n. And then in 2020, in several papers, it was shown that in fact you can go far beyond the square root barrier. And what is important let me summarize some important ingredients of this construction. So actually, this was the idea of using high-dimensional expanders, tensor product of complexes over group algebras, and symmetric Tanner codes. And actually, in our paper, we use all these components. Okay, let me also describe locally testable codes. So the idea of the locally testable code is a code where you can have a probabilistic tester that allows you to test whether a bit string is close to the code space or not. And in our work, we use a very simple combinatorial definition that corresponds to a rather strong form of local testability, and we call it VS locally testable. We call a code VS locally testable if each row of the parity check matrix is bounded from above by W, and we also have this inequality, which actually says that if the syndrome is small, then the distance from the bit string to the code is also small. What is important that about this locally testable code, that they usually have checks that are really, really redundant. Take for example, the famous Hadamard code. From its definition, we see that it has length 2 to the n, but we can see that it have 2 to the n by 2 to the n checks. So it means that the number of checks is much more than needed, which suggests that these checks are really redundant, and we can also consider some meta checks on checks. To be honest, I'm not aware of any practical applications of locally testable codes, but they are really, really important in theoretical computer science, since they implicitly appeared in the proof of PCP theorem. And locally testable codes, I should also say that locally testable codes with almost optimal parameters were known to exist for a long time. This is in high contrast with qLDPC codes. And the main problem here is similar. So are there any good families of locally testable codes? And the main results of our paper that show that both these conjectures are true. And I should also say that results similar to our theorem one was also independently obtained by Dinur, Ever, Livne, Lubotsky, and Moses, and the result is a little bit more stronger, since they obtain codes with rate arbitrary close to 1. And I should also say about some very recent work that also shows that it is possible to use lossless bipartite expanders to obtain locally testable codes, and some other interesting constructions that possibly can even give you quantum LDPC codes with linear time decoder. Okay, let me describe our main ideas, and in order to do this, we need a notion of chain complexes. So a chain complex is a collection of vector spaces and linear maps between these vector spaces, such that if you apply two consecutive linear maps, then you obtain 0. And this allows to consider the space of boundaries. For example, if we apply this map to this space, then we obtain the space of boundaries as images. And if we consider the kernel of this map, we obtain the space of cycles. And the quotient of these two groups is called homology group. And you can see that, in fact, you can convert this, you can consider this homology group also as a metric space, because these homology classes are just cosets, and in exactly the same way as we did before for quantum LDPC code, so we can consider the quotient Hamming distance for them. And why these chain complexes are important? They're important because we can describe classical and quantum LDPC codes as chain complexes. In fact, classical LDPC codes can be just identified with a two-term chain complex, where one term corresponds to bits and another to checks. And quantum LDPC codes can be described by a three-term complex, where we have three terms that corresponds to three parts in the Tanner graph. And I should also say that this property, this commutativity condition, is just equivalent to this condition of a chain complex. And in some sense, we can view we can identify three-term chain complexes with qLDPC codes, and you can see that the distance is related with this quotient Hamming distance for these metric spaces. Okay, let me describe the idea of lifted product codes. Okay. In order to describe it, let us first describe what is a lift of graphs and codes. So the idea is very simple. We start from very small graph, which we usually call a base graph, and we usually have a very, very large group, for example, of the size L. And we obtain a G-lift of this graph if we assign to each edge some element of this group. And we actually obtain L times larger graph using the following idea. So we just replace each edge here by perfect matching that corresponds to this element S, to this permutation. You can see this idea on this example, where we obtain 3 times larger graph using G-lift, where G is equal to the cyclic group of 3 elements, and here just our shifts. And of course, we can also apply this idea to codes as well, because every code is defined by its Tanner graph. And if we apply a G-lift to a Tanner code, we obtain a G-lifted code. And what is known about this G-lifted idea, that the lifted graph is the same as a graph with a free action on vertices and edges, and G-lifted code is the same as a code with a free action of a group G on the bit positions. And the very famous example of G-lifted code is the so-called quasi-cyclic codes, where G is just a cyclic group. In fact, almost all classical LDPC codes that are used in practice, they are quasi-cyclic LDPC codes that obtain as lifts from one small base code. And it is quite natural to ask whether we can do something similar in the quantum case. So we can start from very small quantum code, and we want to lift and obtain large code. And unfortunately, it is not clear how to do it for general quantum codes. But luckily, we can always do it if this quantum code is obtained as a product of two codes. And the product of two codes, it's a different name. It's a hypergraph product. Okay. Let me describe the idea of the product of two graphs. So first, let us consider the topological direct product. So we consider graphs as topological spaces, and they are one-dimensional complexes. And if we multiply them, we obtain a two-dimensional complex that contains vertices, edges, and two-dimensional squares. And here, of course, we use this straightforward multiplication table. In computer science, people usually work not with this construction, but with the Cartesian product. In Cartesian product, we just remove these squares and obtain just use one skeleton of this complex. And the idea of the G-lifted product construction is as follows. So we start with a standard product. Yes, and then we lift this graph using left lifts. By left lifts, I mean that these shifts are multiplied from the left, and then we lift this graph using right lifts. By right lift, I mean that these shifts are applied on the right, and using this left and right lifts, we can obtain actually the lift of this two-dimensional complex. We can lift each square into several copies of these squares shown here. Okay. We can also consider this on this example. So we can lift this graph and obtain this two-dimensional complex. And we also need a Cartesian kind of product. So we can also leave the Cartesian product, and so here it is essentially the same operation, but we just consider one skeleton. Okay, now we have lifted product construction for graphs, and we can apply it to codes. Suppose we have two classical codes defined by the Tanner graphs, and we can apply the standard Cartesian product and obtain what is called the hypergraph product. And this hypergraph product can also be described by this complex. Okay, now we can lift these classical codes and obtain lifted Tanner graphs. And then we can apply our lifted product construction and obtain these new lifted Tanner graphs. And this would define what we call a lifted product code. And this lifted product code can also be described algebraically using this diagram. Okay, let me describe our main construction for good qLDPC codes and locally testable codes. So we start from two lifted graphs. And these two lifted graphs are obtained as two lifts of Cayley graphs. And in order for construction to work, we need Cayley graphs that are good spectral expanders. And particularly in our work, we use LPS family of Ramanujan graphs. And if such a graph is a good spectral expander, then it is also the obtained two lift is also a small set expander. Now we apply our lifted product construction and obtain two-dimensional complex. But these are all graphs, but we need codes. How we define codes? We use Tanner graph idea. So Tanner code idea. So a Tanner code is just a code defined on a graph where our bits sits on edges, and for each vertex we have a local constraint, local code, and we assign these local codes and obtain a Tanner graph. And in this case, it's a lifted Tanner code because we apply it to the lifted graph. And we also do here, and here we obtain what can be called a two-dimensional Tanner code, because here we have our constraints are not classical codes. Our constraints can be viewed at each vertex can be viewed as a quantum codes. In fact, they are just hypergraph product codes. And for our construction to work, we need a pair of local codes with special properties that we call product expansion, which is in fact is equivalent to the robustly testable property from the field of locally testable codes. And we also require that the distances of these two codes should also be high. Okay, let me briefly summarize the idea of our proof. So it is based on the concept of local minimality. So let us consider the Kitaev storic code. Here we have an example of one chain that cannot be reduced. So its weight cannot be reduced by any boundaries. And we call such chains minimal. But here we have another kind of one chain. So this one chain can be reduced to zero if we add the boundaries of these four squares, we obtain a zero. So this is not a minimal one chain, but in fact, this one chain still cannot be, its weight cannot be removed by applying just one boundary. And we call such chains locally minimal. And if we denote by this value the minimum weight of a non-zero local minimum one cycle, then we have the following fact. If we interpret this complex as a this part of the complex as a code defined by this parity check matrix. So here we have bits and here we have checks. And if we have some bit string and we apply a parity check matrix to it, then we obtain a syndrome. And if this syndrome is sufficiently small, this fact means that we can locally decrease its weight. And in fact, we can decrease it down to zero. So in effect, we obtain something similar to bit flipping decoder. And using this idea, it is possible to show that if a chain complex have this property, then the code defined by the kernel of this matrix and the code, the quotient code defined by these two parity check matrices have linear distance. So this code is locally testable, and this code has good distance. And in fact, this was these ideas were already used in the literature before. And let me summarize our main results. So given a G-lifted graph and the parity check matrices HA and HB, if our graph is a small set expander, and if our couple of codes is product expanding, then the obtained three-term chain complex has the property that this threshold value grows at least grows with the group size. And now if we start with a constant size graph and lift it, then we would obtain that this value grows linearly with the size of the code. And actually, this what allows us to prove our main, the most difficult parts of our main results, the property of locally testable in theorem 1 and the distance in theorem 2. Okay, what's next? In our current paper, we deal with these three-term complexes, and we proved they have these properties. But what if we consider a more general complex with 5 terms? And in fact, it follows that if we have similar properties for these 3 levels, then one could obtain not only good classical LTCs and quantum LDPC codes, one could also obtain quantum locally testable codes, which also implies the NLTS conjecture. And we can also show that this complex this code has linear time single shot decoding.